Hey, in today's video we will see what topological periodic homology, the THH analog of the periodic homology we saw in ordinary Hochschild homology is, how to define it in terms of the Tate construction, and we will see how to compute it in the special case of HFP. I'm Achim Krause from Mathematics Münster. So TP, topological periodic homology, is an analog to HP. We defined HP, periodic homology, by inverting a specific element in negative cyclic homology. So it may come as a surprise that TP is not in general defined by inverting an element and is in fact not necessarily periodic at all. So what is the definition? Well, similar to how we defined topological cyclic or negative topological cyclic homology as homotopy fixed points, TP is defined using the Tate construction with respect to the S1 action here. And it enjoys similar formal properties. In particular, it's also multiplicative, like negative cyclic homology was. So this is just due to the fact that the Tate construction is lax symmetric monoidal in a way that is compatible with the lax symmetric monoidal structure on homotopy fixed points. Right, and so in particular, there's a map from negative cyclic homology, which is S1 fixed points on THHR, to TP, which turns TP into an algebra as long as R is commutative. Right, so TP is a TC minus R algebra if R is commutative. And you can still say things such as if R is just En, then these will be En minus 1 algebras, just due to the fact that THH is then an En minus 1 algebra. But in general, for associative algebras, all these things are just spectra. Right, and so how would we compute this? Well, it turns out we can do a similar thing as we did for negative cyclic homology, namely, negative topological cyclic homology, I should say. Namely, there's a spectral sequence. So for spectra X with G action, there is, or there is a multiplicative spectral sequence which is, multiplicative conditionally convergent spectral sequence. And again, like in the negative topological cyclic homology video, it's not too important to understand what conditionally convergent means. It leads to some subtleties when it comes to deciding whether the spectral sequence actually converges. But just ignore that. Multiplicative means, as for the homotopy fixed point spectral sequence, that if you plug in a ring here, namely an algebra in spectra with G action, then you will get a multiplicative spectral sequence. And the fully general statement you can make is that there's some kind of external pairing between the spectral sequence for X and the spectral sequence for Y, taking values in the spectral sequence for X tensor Y. That's why I just say multiplicative here in general, because there's this external pairing. Okay, how does this spectral sequence look? Well, it's very similar to the homotopy fixed point spectral sequence that we considered. Namely, its E2 page is obtained by applying the functor we're studying, so now that's not homotopy fixed points, but Tate, to Eilenberg-MacLane spectra given by the individual homotopy groups of X. And this converges to the actual homotopy groups of X Tate G. And it's constructed in a similar way, right? And I'll just give a proof sketch here. It follows a similar idea, which is that we have the Whitehead filtration. Tau bigger equal bullet X on X, right? That's a filtered spectrum. And now we can apply the functor Tate G, right? Since these truncations are just, we're post-composing our functor from BG to spectra with truncation, all of these are still spectra with G action. And so we can apply Tate and this again produces a filtered spectrum whose associated graded terms are now the result of applying Tate G to the individual Eilenberg-MacLane spectra that appear in the Postnikov tower of X. That's where this E2 page comes from. And then the multiplicativity, similar to what we skipped over in the construction of the homotopy fixed point spectral sequence, the multiplicativity follows from some multiplicative properties of the Whitehead filtration. And this statement about convergence, that follows after checking a bunch of more subtle things, which is that somehow this functor here doesn't generally commute with limits or co-limits, but one can check that in this case of the Postnikov tower, it commutes with the limit and the co-limit of the Postnikov tower. This uses some connectivity properties. I'll not go into that. So that's nice and all, but it still doesn't enable us to compute anything, right? So we would need to understand Tate S1 of Eilenberg-MacLane spectra. And that's what we're going to try now. So let's start with the most basic Eilenberg-MacLane spectrum, HZ. And now we will focus on the case of the group being S1, because that's what appears. But what we're doing here actually can be generalized to cyclic groups. And I'll say something about that later. So for HZ and group given by S1, we can try to compute the Tate S1, the Tate construction, by the defining cofiber sequence. So we consider the cofiber sequence given by homotopy fixed points, the Tate construction, and then what comes in here is the norm And in full generality for compact Lie groups, the norm, so for discrete groups, I would just put the homotopy orbits here. For compact Lie groups, the homotopy orbits here are kind of twisted, namely by the representation sphere of the adjoint representation. So I would write something like add G tensor HZ and then HG. But observe that G, in this case, is an abelian Lie group, right? So the adjoint representation is just trivial. So this guy here is just S1, since G is one-dimensional, with the trivial action. And so this here is just sigma lower homotopy orbits, right? Because then this just means that this is just the suspension of HZ with the trivial action, and I can pull the suspension out. Okay, and sorry, I should write S1 here instead of G. Right, so we have this cofiber sequence which involves homotopy fixed points and homotopy orbits, but there's a shift here. And then you have this norm. And now the homotopy fixed points somehow only have homotopy in non-positive degrees, and the homotopy orbits only have homotopy in non-negative degrees. So this map actually doesn't do anything. And from this you can read off the homotopy groups of this guy. And I recommend you do this as an exercise. So determine the homotopy groups of this. We're not yet talking about ring structures, just additively what they are in each degree. And if you don't want me to spoil the answer for you, you should maybe pause the video and think about this a little bit, because we're now gonna use the result. So what is the result? Well, from the sequence, we can get that this is Z for star even. So it's Z in all even degrees and 0 in odd degrees. Right? So it kind of, at least additively, it does look like a periodic version of cohomology, right? Cohomology was polynomial in a degree -2 generator. Now we have things all over the place. And in fact, this is exactly what happens. Okay. Right, and this is a description as an algebra over the homotopy groups of this guy, which in the negative topological cyclic homology video we discussed was Z adjoint T with T in degree -1. So this is that T, and you can get the homotopy groups of this guy as a ring just by inverting that T. Okay, so how would we check that? How do we get at the ring structure? Well, one very nice trick that you might have seen with the Serre spectral sequence is that you can sometimes apply a spectral sequence in a situation where you know what it converges to, but you can work your way backwards. And if we recall one of the key properties of the Tate construction was that it annihilates things whose action is induced, so to say, free modules. So in this case, we consider the Tate spectral sequence for the S1 spectrum with S1 action, HZ tensor sigma infinity S1. So this is induced in the sense that I was just referring to, right? Because it comes from just the spectrum HZ by tensoring with the free S1 module. So this is exactly what this induction does. The left adjoint to the forgetful functor from spectra with S1 action to just spectra. And we know, therefore, that Tate S1 of this guy is 0. So how does the spectral sequence look like? Well, we know already additively what the Tate construction on Z does. And what are the homotopy groups of this guy? Well, the homotopy groups of this guy are just the homology groups of S1. So they're just Z in degree 0 and 1. So my spectral sequence looks like this. I have Z's in degree 0 and 1. These come from the homology of S1. And then, like for the homotopy fixed point spectral sequence, I have these Z's coming off to the left in these even degrees. Sorry, I'm messing this up. These are alternating Z's and zeros. But then, so this is what we would get in the homotopy fixed point spectral sequence. But then here we said we have Z's in every degree, not just negative ones, in every even degree. And so this continues to the right, like this. Okay, and in the formula I gave 2 boards ago for the spectral sequence, I had these gradings P and Q, so these are the gradings. This is still homological Serre grading. Okay, and so in particular differentials go 1 to the left and 2 to the left, 1 up. The first differential at least. And in fact, if you think about it, there's only one way for all of this to become 0, which is after the first differential, because all other differentials are too long and either end up in this desert of zeros up here or come from these zeros down here. So in other words, knowing that this becomes 0, we know that all of these maps here are isos. So this is how the spectral sequence looks like additively. And now, here comes the trick. We can also use multiplicative structure on this. Now, we don't have a ring structure on this guy as an S1 spectrum. You could put a ring structure on it using like the group structure on S1 just as a spectrum, but that's not going to be S1 equivariant. And if you think about it, you know this from this picture already, because if this were a ring and the generator of the C here would be named 1, then this differential would very much violate the Leibniz rule, right? You just look at the differential on 1 squared, which is also 1, and you get some contradiction. So this is not a ring, but it's a module over HZ. And so the Tate spectral sequence for Hz acts on this spectral sequence. But the Tate spectral sequence for Hz itself is just, it degenerates. This guy is already Eilenberg-MacLane. So let's see what this tells us. So let's describe this stuff here as a module over the Tate construction on Hz. So we fix generators xi of pi 2i Hz Tate S1. Right? We don't yet know what the multiplication is. Xi times xj will be some multiple of xi plus j. But additively, it's just free on generators xi, right? We're just fixing generators for these guys. And now we also fix generators sigma 0 and sigma 1 of the homology of S1, which is these groups here, the homotopy groups of this guy. And we could be tempted to just call this sigma 0 1, but that would be very confusing because, again, this guy is not a ring. So let's just really call this just sigma 0. So in this picture, the generator in degree 2i comma j is now given by xi times sigma j, right? I have like x0 times sigma 0 here and x0 times sigma 1 here, and in all the other degrees I get similar like products. Like here I get x minus 1 times sigma 0 and so on. So this is how this is a module over the homotopy of the Tate construction on Hz. And what does the differential tell us now? Well, we know d2 of sigma 0 right, sorry, I forgot to say what I was going to say here. I want to fix one thing, namely that x0 is 1. Right, the homotopy of Tate S1 on Hz, that is a ring, so that's something I can do. In general, we know even preferred generators for these in negative degrees, right? Because this map here was an isomorphism. So we could already say in negative degrees, we just call our generators t to the I or something like that. But I don't think I need that here. But yeah, maybe let's do that. That might make it easier. Okay, so I have these generators sigma 0, sigma 1 in the homology of S1. And then I'm going to say here with xi, x minus I given by t to the I. Right, so in negative degrees, these are powers of t. Right. So what do we know about d2 of sigma 0, which is this generator down here, which I could also write as x0 times sigma 0. Well, it's going to be a generator of this guy, right? So it's plus minus x minus 1 times sigma 0. Or in this case, I've already called this t. So it's plus minus t times sigma 1, right? That's what generates this guy, x minus 1 times sigma 1, or t times sigma 1, as we called it now. And of course, the precise sign you get here depends on conventions. This is how this element T that we fixed in the homotopy fixed points is related to the choice of a generator sigma 1 of homology of S1. And so if you pick your conventions correctly, you're going to get +1 here. So if we have this, well, what do we get for any other of these entries? Well, any other of these entries is of the form xi times sigma 0. The xi comes out of the homotopy groups of the Tate construction on Hz. So, for example, since the Tate construction, the Tate spectral sequence for Hz just degenerates, the differential on this guy is 0. On this guy it isn't. So if I use the Leibniz rule, and this is now the Leibniz rule for the pairing between Hz and this guy, then I get xi times, and now d of this. So plus minus xi times t sigma 1. But we also know, since these differentials are isomorphisms, that this guy here is also plus minus 1 xi minus 1 times sigma 1, right? Because it has to be a generator in the respective degree. And the sign we're getting here might be different from the sign we got here. Again, it depends on how we fix these generators xi. But it certainly tells us that xi times t is up to a sign xi minus 1. And now we just choose these generators xi such that all signs are plus. And then what do you have here? Well, you have some ring which, as a graded abelian group, is free on these generators xi, and it's also a module over the polynomial ring in T in such a way that multiplication with T gives you, like, takes one generator to the previous one. And if you think about it, that's precisely what this guy is, right? This exactly identifies this. So we get that these homotopy groups here are simply this ring. So the overall structure of the argument was simply that we have this spectrum here on which Tate vanishes and whose Tate spectral sequence only has these two lines, both of which are a free module over the ring we want to understand. And then we use the multiplicativity with respect to this action to figure out how the ring structure looks like. It's a little bit like if you would deduce the ring structure on the cohomology of Kz2 from the cohomology of Kz1 with the Serre spectral sequence. All right. So, and in fact, at this point, I want to give a little exercise. So we will also, at some near point in the future, need to talk about the Tate construction with respect to a cyclic group. And I claim that you can compute the ring Hz Tate Cm where m is some integer, right? So for some cyclic group, similar to how we computed this here, first discussing how it looks like additively and then using a special version of the Tate spectral sequence to compute backwards. And I want to give that as an exercise. It's really similar arguments. The only difference is that you won't need the free action here. You'll need to talk about something slightly different. And I'll give a hint. Try to find a nice free action on a space with suitably easy homology of Cm. All right. So now that we know that this is simply this kind of Laurent polynomial ring, this inverted polynomial ring, let's remark something, which is that if you do the same argument with HA tensor sigma plus S1 as HZ module, we get that the homotopy groups of HA Tate S1 are simply like this. And the same remark as in the negative topological cyclic homology video applies, which is that, of course, this notation is a little bit weird if A is just an abelian group. But what I mean by this is that it's simply the module, which is like A in every even degree, and T from this ring, T acts as the isomorphism that shifts everything around. But of course, this description is also valid if A is a ring, right? If A is a ring, then this is an algebra, and then I claim this is even the structure as an algebra over this ring here. Right. And so this settles what goes on for Eilenberg-MacLane spectra. So it kind of already tells us what happens for it gives us some control over how the Tate spectral sequence looks like. But before I discuss that, let me first tell you something about how we can generalize what we saw here. And so the generalization is that if X is an object of fun BS1 mod HZ, so an HZ module together with a BS1 action, with an S1 action, or equivalently an object of, a module over HZ with the trivial action in the category of spectra with S1 action. It's a little interchange trick you can play here, but it's more than just being an HZ module and then some action just as a spectrum. So in some sense, both of these encode that the action has to be Hz linear. So if you have that, then you can write x tight S1 in terms of x HS1 by tensoring over the homotopy fixed points with the Tate construction here. And another way of expressing this, kind of a similar way, a little bit of a weaker statement, but it gets the point across, is that the homotopy groups of this guy are obtained from the homotopy groups of these homotopy fixed points by inverting the element T. And so in some sense, you should think of this spectrum here as obtained from this spectrum really by inverting the element T. We haven't talked about how the how to invert an element in the ring spectrum, but if we had, we could also say here that you can obtain this ring spectrum, this commutative algebra, by inverting an element T in this one. All right, so here's a proof sketch. So we can write HC Tate S1 as a filtered colimit, HC HS1, and then there's a map multiplication by T, which goes to sigma 2 HC HS1, and then we do multiplication by T again, that will go to sigma 4 HC HS1, and so on. And this is an expression as HC HS1 modules. And one way to see this is you simply write down a map, and the map will be multiplication with suitable powers of T, suitable negative powers of T. And then you just check that it's an equivalence. So maybe I'll pose that as another exercise to check this, to be sure. So once we know this, if you tensor this, so this, by the way, yeah, right. So if you tensor this expression here with XHS1, we see that we need to show that X Tate S1 is the same kind of colimit. Right. So we have a map, and all we need to check is that that map is an equivalence. And whenever you're in a situation like that, you have a natural transformation, you want to check that it's an equivalence, you can try to reduce that to special cases, simpler objects. And in fact, so what you can do here is you first see that this works for X Eilenberg MacLane by what we observed in this remark over there. And both sides are compatible with fiber sequences. Right, since the homotopy fixed point and the Tate construction, they're exact functors. So they commute with fiber sequences. And so is this filtered colimit. So using the Postnikov tower of X, if X has only finitely many non-trivial homotopy groups, you can actually use this to reduce, to inductively get this from the Eilenberg-MacLane case. So this already, these two together already prove the statement for all spectra X which have finitely many non-trivial homotopy groups. And now this last part now is why it's a sketch. I'm not going to talk about how to extend this to all of them. So to extend to all X, need some connectivity arguments. Right, so the problem here is that you can of course take the Postnikov tower of X that expresses X as a limit and colimit of like co-connective or bounded above and below spectra. So you can kind of reduce to the case of X with finitely many non-trivial homotopy groups that way. But then you have to check that both sides of this expression here commute with that limit and that colimit. And again, as I said, for convergence of the Tate spectral sequence, this is not completely obvious here, and it's also not completely obvious here because colimits don't commute with limits in general. But in both cases, you can get that by thinking about connectivity of these diagrams in a certain way. I'll not say more. All right, so something that, of course, is kind of suggested in the notation, but which we haven't seen yet is what does this TP guy have to do with HP? Well, here's the good news. Similar to negative cyclic homology, HP arises from HH in the same way that TP arises from THH, namely by taking the Tate construction. And, well, how's the proof? Well, since HHR is equivariantly an HC module, HHR Tate S1 is obtained from HHR HS1, which was our definition, or which we in the negative cyclic homology video saw to coincide with negative cyclic homology by inverting the element T. Right? That's precisely the content of the previous lemma. And if you recall back to our video on periodic homology, this is exactly how we defined HP. We defined HP by suitably inverting this element T in HC minus. So it coincides with HP. So in particular, this warning I made in the beginning that, well, TP is not necessarily periodic. In this HC linear setting, that's not yet a problem, right? Ordinary HP is really periodic and so on. I'll say more about that in the end. All right. So what about TP? Well, let's go back to the Tate spectral sequence. And as we now know, let's maybe call that a proposition at this point. The Tate spectral sequence, which we saw earlier kind of in an abstract description, which was just, oh, its E2 page is certain Tate constructions of Eilenberg-MacLane spectra. For Tate S1, it takes the form pi star x and then adjoint t plus minus 1, and it converges to pi star x Tate S1. Right, so in particular, we can apply this to THH to get a spectral sequence that goes from, and let me maybe write this out, THH star R adjoint this class T plus minus 1 converges to TP star R. Similar to how we had a spectral sequence like this without the negative exponents of T for Tc minus. So at least on the level of spectral sequences, the Tate spectral sequence really looks like a periodized version of the homotopy fixed point spectral sequence that we previously considered. And so very much along the lines of what we did for Tc minus, we can also now compute the case of Tp of Fp. So the claim is that the homotopy of Tp of Fp is really just this kind of periodic thing. And how do we prove that? Well, we can't directly apply the theorem or the lemma we proved previously on these HZ modules, because although THHR or THHFP is an HZ module, it's even an HFP module, that's not necessarily compatible with the S1 action. It is in fact true that it's equivariantly an HZ module, but that uses some subtle tricks, and so we won't rely on that here. In general, taking the S1 action gets rid of this kind of linearity. For example, obviously, it can't be equivariantly an HFP module, because then Tc minus and Tp would still be Fp modules, which they clearly aren't, right? So it's subtle. Like I'm telling you, it's true, but it's subtle that these things are still HZ modules, and that doesn't hold for more general rings here. So instead of directly appealing to that, let's just observe that the Tate spectral sequence is simply a periodized version of the homotopy fixed point spectral sequence. Right, so at least on the level of E2, this works, right? The E2 page is really just obtained by inverting T. And it still degenerates, either because it's obtained by inverting this element in the degenerating homotopy fixed point spectral sequence, or I guess for the same degree reasons. Everything is in even degrees. Right? So what does this look like? Well, let me again draw a picture. For the homotopy fixed point spectral sequence, we had all these FPs, right? And we had here this element x, x squared, and so on, and then To the left, we had FPs on T, Tx, Tx squared. Here we have T squared, and so on, right? So this all degenerates. All what we had to do for our computation was to check that these terms here are kind of a sequence of non-trivial extensions where the element 1 in here, if I multiply it with p, I don't get 0, I end up here in the actual homotopy groups, and I get Tx and so on. So these together were Zp, which is just filtered by powers of p, and Tx in there was actually p, at least up to a unit which we defined away. Now what happens here? Well, this guy will have this element T inverse. T inverse x. T inverse x squared, and so on. So this is now periodic in both directions. And so morally what happens in here in this identification is that the extension problem we solved here, this gets now kind of periodically transported all over the place. So this diagonal here again gives a Zp on the element T inverse, and so on. So what's a way to say this cleaner? Well, first of all, note that we have a map from Tc minus to Tp, and that's compatible with these spectral sequences here, right? Both were obtained by doing the same kind of filtration. So there's a map from the homotopy fixed point spectral sequence, which is just this area, to the whole thing. And that's compatible with the map from Tc minus to Tp. So in negative degrees, this diagonal, this diagonal, this diagonal, it's just an isomorphism, right? So in negative degrees, we have pi minus 2k of Tp, Fp, is the same as pi minus 2k of Tc minus Fp. i.e. polynomial, i.e. Zp on an element T. And maybe at this point I'll call this element T tilde. It's a little bit sloppy to call this T up here maybe, because there's only a well-defined element T down here on the E2 page, right? This comes out of the Tate construction on Hz. So it gives you a well-defined element T in the Tate construction of every ordinary, like Eilenberg-MacLane ring. But even though this degenerates, there's not necessarily a canonical choice of this T in pi minus 2 of Tc minus. So let's call this T tilde, and remember that we're making a choice of some element that maps to this guy on the E infinity page. And then we're getting from our argument with the homotopy fixed point spectral sequence last time that powers of this, that all the terms here are generated as Zp modules freely by powers of this T tilde. We can also choose a representative in pi 2 Tp of this element T inverse. And I'm going to call this representative T inverse tilde, but note I'm putting the tilde, I hope that that's kind of notationally possible to distinguish. I'm putting the tilde over the T inverse to signify that we don't yet know at this point that it's actually inverse to T tilde, right? We've just picked some representative of this element. But if you look at what you get here, tau tilde times tau inverse tilde is, by the ring structure here, the element 1 modulo higher filtration, right? It maps in the infinity page to 1. So this is 1 modulo higher filtration. So T tilde times T inverse tilde is a unit. And now this tells you that T tilde is invertible and the negative powers tau tilde inverse to the minus k generate sorry, let me go here, generate pi 2k Tp. Right, so this will be Zp adjoint this element T tilde plus minus 1, and keeping in mind that this is not 100% well defined, that this depends on a choice, we're calling this T in what follows. All right. So this proves what I wanted to say about TPFP. And note that this even tells you a little bit more. It also tells us what this element X maps to, right? So in both cases, TP and TC minus, we saw that they're just additively just ZP in every even degree. But what is the map doing between them? So there's the canonical map, the natural transformation from homotopy fixed points to Tate S1. It, well, on negative degrees, TC minus was generated by powers of T. So on negative degrees, it's an isomorphism. But in positive degrees, TC minus is generated by this element X. And if you look like here, these, this diagonal here, that's the associated gradient of a ZP. The X lands in here, in filtration 1. So it's some multiple, it's P times, it's some unit multiple of P times T inverse. And in fact, if we fixed conventions as we did, that Tx is actually P in Tc minus, then of course you get that in Tp, X is P times T inverse. So this canonical map from Tc minus to Tp, in negative degrees, it's an isomorphism. In positive degrees, it's multiplication by P to the k in degree 2k. And we'll see when we talk about Tc that there's another map from Tc minus to Tp. And it's the interplay of this canonical map and the other map that gives rise to Tc. Finally, I wanted to say something about this warning that I made in the beginning, that Tp is not necessarily periodic. So in all the cases we've considered now, we were lucky and it was periodic. But as soon as the Tate spectral sequence has differentials, which it didn't have here for degree reasons, it can happen that you have a differential on this element T. So you have this 2 periodicity on the E2 page, but then after the first differential, it might be less periodic. You might only have T squared surviving to the next page, so it would only be 4 periodic anymore. And in fact, there are examples where you get these infinite families of differentials, and even examples where the resulting thing becomes connective. So this is something to keep in mind, that although from this picture these state constructions look very periodic, if I apply them to general spectra and not just Ironberg-MacLane spectra, everything can happen. They're typically not necessarily periodic. All right, that does it for today. Thanks for watching and see you next time.